So far, we've been able to rely on the central limit theorem and assume that x bar, the sample mean, is normally distributed. It requires a couple things, however. It requires that we have to have at least one of the following: that we know the population standard deviation sigma, and or that we have sample size greater than 30. Now, we hardly ever know population standard deviation. In fact, if you think about it, if we know population standard deviation, we probably know population mean, and we're not needing to estimate it. So that's really rare that that happens. And for n to be greater than 30, often it's not. Often n is less than 30. So we need to have some alternate distribution to use for x bar. Now, if we don't know sigma, then we can calculate S, the sample standard deviation, and use that instead of sigma. But just like x bar, S is a random variable because it's based on a random sample. So it's going to change from sample to sample. It's not fixed like sigma. So remember, sigma is a fixed value, not random. So not adding any variability to the estimate, but using S is going to increase variability. All right, so that means that when we estimate a population mean under these circumstances, we have to account for that variability by having a wider confidence interval. In other words, less precise. So instead of using the normal distribution, we are going to use a different distribution. It is called the student's t distribution, and it is based on a statistic that we call t. So if we have a scenario where n is less than 30 and or sigma is unknown, in this case, sample size is maybe not large enough to counteract the variability that we introduce by having S instead of sigma, and we can't use a z-value, all right? We can't look up in the z-probability tool to get that z-value. So like 1.96 isn't going to work, 2.575, 1.645. We have to throw those out. All right, those are based on the normal distribution, and under these circumstances, we cannot assume x bar is normal. So we're going to assume, though, that it has a student's t distribution. So we got to introduce this distribution. So again, t is a random variable, so it has a PDF in terms of a table, a function, and a graph, just like all the other random variables that we've looked at. So x bar is the mean of a random sample of size n from the original distribution being normal or close to normal. That should say close to normal. With mean mu, then the random variable t equal to x bar minus mu over s divided by square root n has a t probability distribution. So the only thing that's different here is that we're using S, the sample standard deviation, instead of the population standard deviation to calculate that t value as opposed to a z value. So like other distributions, the t has a value that defines it uniquely. So if you remember back to binomial, n and p defined binomial. Uniform, the minimum and the maximum value defined the uniform. And for normal, it was mean and standard deviation. So for t, it's uniquely defined by what we call the degrees of freedom. And the degrees of freedom, we use df to stand for it, and it is just the sample size minus 1. So it's just one single value. All right, we can represent the PDF, the probability distribution of this random variable in this three same ways we have the others: function, a graph, and a table. We're not going to look at the function. It's beyond what we are doing in this class. But we can look at the curve, and then we will use an online tool to access values out of a table. Let's look at the density curve for t. So remember that t is defined by taking some sample mean x bar, subtracting the mean of the original distribution, and then dividing by s, the sample standard deviation, over the square root of n, the sample size. Okay, so this density curve is centered at 0. All right, so like z is centered at 0. And its shape is similar to the normal in that it is symmetric. And it has that bell shape, like the normal, where it is higher in the middle and lower on the ends, and in the extreme it has tails. All right, it differs from z, or from the normal, in that it is more spread out. Okay, it's more variable, it has larger variance. And as n increases, the spread decreases. So again, larger n, it affects spread in that way. It makes things narrower. The total area under the density curve, just like all others, is 1. And the probability that t is between two values is the area under the curve between those two values, just like for other density curves. Okay. All right, you can see the picture there of the density curve. All right, that flattest one is a t distribution with a small sample size, less than 30. And then that middle one, you can see as n gets larger, in this case getting closer to 30, it is getting less spread out. All right, it's more concentrated around the center, around the middle, their mean. And then you see the z distribution. You can see it's even less spread out, all right, than those other two. So let's look at the confidence interval then for using the t distribution. So it's going to start off the same way. We take x bar, and then we're going to add and subtract the margin of error. Now here's where we would have the z value, but since we can't use z, we're using t. And like the z, we identify it by the area to the right of the curve, right, of that value under the curve in the tail. And then we also have to identify the degrees of freedom, n-1. Okay, so that will be a unique value of t dependent on the confidence level and also the degrees of freedom. Okay, so it's not just one value for a given confidence level. It's also going to depend on the degrees of freedom, which is going to change from application to application. And then that's multiplied by s over square root n. Okay, so the differences we have here then are we've got s instead of sigma, and then we have that t value in there instead of a z value. Okay, so let's identify what we mean by that t value with those two subscripts. It's the t value corresponding to an area of alpha over 2 to the right of it. So it would be like this is the t value, alpha over 2 comma n-1. Okay. Okay, to get the probabilities, to get this t value, you're going to use the probability distribution tool for t values that is posted on Foxtail. Okay, so go ahead and take a look at that. I've posted a short video on how to use it. It works really similar to the normal probability distribution. So you might want to pause right now, go watch that, and then come back and watch the rest of this video on 8.2. Okay, go ahead and take a moment to read this problem, and then we'll do this together. Okay, we're eventually going to be asked to construct a confidence interval here. So it's helpful to identify all the things that we're going to need to be able to do that. So we're going to want to pick out x bar. So we're told that these 25 Americans that were surveyed, watched on average 151 hours each month. So our x bar, our sample mean, is 151, and the standard deviation of 32. Sample size is 25, so that means degrees of freedom is one less than that. It's 23. Okay, define the random variable x in words. Okay, so x is the random variable that is measuring the number of hours of TV watched per month. By a single American, or one individual American. Okay, so we can think of that as like the underlying distribution is the number of hours of TV watched by one individual American. Now we want to define what we mean by X bar. Well, X bar is the mean number of hours of TV watched per month for the 25 Americans surveyed. Okay, so the key is there, it's X bar, so it's a sample mean, so it's a mean number. Okay, we want to determine what distribution we need to use for this, and we got to look down here and see, okay, we're constructing a 99% confidence interval for the population mean. Okay, so it's either going to be normal or it's going to be t. And if we look back up, we see that we don't have sigma, and n is less than 30. So that's the combination of things where it says we are going to use t, and that is because n is less than 30 and sigma is unknown. Okay, we can now find this confidence interval. So we're going to take X bar, add or subtract the t value that has area to the right of alpha over 2, so that's going to be 0.005, and then also depends on the degrees of freedom, which is 24. And then that's multiplied by s divided by the square root of n. So filling those things in, we get 151 plus or minus. All right, if you look that value up in, use your t-distribution calculator to find that value, you're going to plug in degrees of freedom of 24. You're going to plug in probability of, if you use the option on the far right with both tails are shaded, you're going to use probability of 0.01, and that should give you a t-value of 2.797. And then that's times the standard deviation of 32 divided by the square root of 25. That gives us a lower bound of 133.1 hours, upper bound of 168.9 hours. Okay, so we're 99% confident that this interval of 133.1 hours to 168.9 hours contains the true population mean number of hours Americans spend watching TV per month. And the margin of error, right, that's just this piece right here, is 17.9. Okay, another example. I would suggest that you go through this entire example on your own and then come back and look at it. As I do it. Okay, so hopefully you've read through the problem and you're able to pick out the following items. All right, we're looking for a sample mean. Well, they had a sample of size 6 patients, and from those 6 patients, they found mean blood pressure increased to be 2.28. and then the standard deviation of that increase was 0.95. All right, one more thing to fill out there. If n is 6, then the degrees of freedom is 1 less than that. It's 5. All right, defining what random variable x is, this is the original population. So x is the number of point decrease in blood pressure, I'm going to abbreviate that, for an individual patient. So that's x, our original distribution. And our x bar, the sample mean, okay, the key here is it's the mean point decrease. For the sample of 6 patients. So the key things for x bar when you're identifying what it is, well, it's a mean and it's a mean of a sample. So you want to include both of those things as you're defining x bar. Okay, we're going to want to come up with a confidence interval for the mean. What distribution are we going to use? All right, well, we're going to use t, and that's because n is less than 30 and sigma is unknown. All right, so the confidence interval, we're going to take the mean value, the sample mean, that is 2.28, add and subtract the appropriate t-values. So the appropriate t-value with a 95% confidence level, we're going to want 0.025 to the right for alpha over 2. And with 6 patients, our degrees of freedom is 5. So looking that value up on the calculator, we get t-value of 2.571. All right, so that's what goes into the margin of error calculation. And then multiply that by standard deviation of 0.95 divided by the square root of the sample size, which is 6. Okay, so we get lower bound of 1.283 point decrease up to an upper bound of 3.277 point increase. Okay, so that is the calculation part. We now want to explain what this means. So a couple ways we can say that. I'll say it this way this time. I'll say there is a 95, all right, that's the confidence level, percent probability that the interval from 1.283 points to 3.277 points includes the true mean blood pressure point decrease. Right, based on a new drug. So due to a new drug. Okay, so the key components in there is identifying the probability. Okay, we could also use the word confidence in there. And then we're associating the probability, right, with the interval. Okay, the probability relates to the interval. okay? And the probability relates to the interval containing the true mean, okay? So that's another piece that we want to make sure we get in there, is that we're referring to the true mean value, because that's what we're trying to estimate here, all right? We're trying to estimate mu, the true population mean blood pressure point decrease. One more question. If the company wants a more precise or a narrower confidence interval, what options does it have to achieve this? All right, there's actually two. So they can either increase the sample size, or what's the other thing they can do? Are you thinking of it? All right, it doesn't say anything about keeping the confidence level the same. So which way are we going to go? Are we going to go to a higher confidence level or a lower confidence level if we want a narrower confidence interval? All right, well, hopefully you're thinking of this. We will, if we want a narrower confidence interval, we decrease the confidence level. Okay, that's it for 8.2.